All right. Hello, everybody. Welcome to the Statistical Foundation for Reinforcement Learning. So this is the eighth lecture of the class. Um, we'll be continuing our topic on exploration, focusing on the bandit setting. Uh, so so let me first quickly address a question that's raised by Jianyu. So as you have seen, I'm a little bit behind the stated schedule on the course website, which says that I'm supposed to be teaching the exploration in tabular MDP, while I'll spend the bulk of the lecture talking about linear bandits, right? So that is not a problem for the schedule of the course, because we'll have some flexibility towards the end of the course on what topics to include and what advanced topic to teach or not. On the other hand, it does create an issue for those who have signed up for scribing, right? So many of you have signed up to scribe due to your special interest in a particular topic. And then when the lectures series are misaligned, then you will, if you stick to the lecture schedule, then you will be scribing for different topic that you originally planned to, right? To address those issue, so we will we will still make use of the original schedule for the scribing. So suppose like you were supposed to scribe for the multi-arm bandit lecture. It doesn't matter whether multi-arm bandit was lecture 6 or lecture 7. And then you'll be scribing for everything, all the materials that I covered, maybe spanning across the 2 lectures on that particular topic. And if you are scribing for the linear bandits, and then this is a lecture of, yeah, we talk about the Lin UCB algorithm in the last lecture, but this is a lecture where most of the materials on its regret analysis will be covered. Okay, so I hope that clarifies this issue due to the course evolving over time. Okay, let's get to the lecture. As usual, we'll start with the quick recap.
Before we start,
Yes.
I just scribed for one of the lectures which has like two parts covered differently, like the RL algorithms and the MDP. Would you want me to redo that?
No. That's perfectly fine. So that lecture is that lecture is actually like added on the fly. It's in particular the RL part of it. I think like your scribe for that lecture is perfectly appropriate, right?
Got
So
it.
when you overlap with somebody else, say in one of these major topics, say with involving like a major effort in writing down the proofs and texting, like writing everything down nicely in LaTeX. Then when you overlap with another student according to the schedule, so you should coordinate with the other student um, who signed up for the neighboring lecture to figure out how to divide the work.
Sure.
Okay.
Thanks.
Yeah, you can find everybody on Piazza and on the on Gaochu Space for everybody who has registered, and then you should be able to find their UCSB email to contact that person. All right. As a quick recap of the last lecture, we talked about the exploration in the simplest possible case, bandits. So in bandits, in particular in stochastic bandits, the only thing that we need to learn is about is what the expected value of the reward is and we can learn that by pulling each arm multiple times, right? And this is an online problem, and the right notion of performance measure for the online problem is a notion of regret. So typically, the regret measures the difference between the performance of an oracle who knows the optimal policy at the beginning and keep playing the optimal policy, comparing to the agent who's uh, needs to come up with the decisions on the fly based on experience collected along the way while balancing exploration and exploitation. And when the regret is sublinear, so say regret is a cumulative performance measure. So for T-step game, then the worst regret will scale linearly in T. So whenever the regret scales sublinear in T, then we consider this agent is running an algorithm that has no regret. So by no regret, we mean that asymptotically, as T goes to infinity, the average regret per step converges to 0. We talked about 3 algorithms: exploration first, epsilon greedy, and upper confidence bound. So all of these all of these algorithms are commonly used in practice. The exploration first, pack all the exploration at the beginning phase of the game. So you explore the different actions uniformly at random, and then collect information about each one of them. And then after that, you basically pre-greedy according to your already learned action. Epsilon greedy tries to distribute the exploration, the uniform at random type exploration throughout the entire horizon of learning. So it behaves very similar to exploration, except that the regret analysis is slightly more involved, which we didn't cover rigorously. The main focus of the last lecture was on the upper confidence bound algorithm, which is a deterministic algorithm. And in this deterministic algorithm, so we are not exploring each action uniformly at random, but instead we, in some sense, just explore just enough to certify that whether this action is sufficiently good relative to the best action by looking at its upper bound of the performance, and if an action's upper bound is smaller than the value of the optimal action, then that arm will no longer be picked ever again. Yeah, so we'll revisit some of the things that we did last time. So we derived regret for the various algorithms. We've seen that in exploration first and epsilon greedy, and the regret is sublinear, but it is slow. It grows at a rate of t to the power of 2/3, with optimal choice of the split between the exploration phase and the exploitation phase, and or the optimal choice of this epsilon parameter to minimize the derived regret bound. On the other hand, the upper confidence bound algorithm, the UCB Bandits algorithm, achieves the worst case square root of t regret, which is optimal in the minimax sense. So there exists a family of problems within the multi-arm bandit problems that any algorithm has to incur square root of tk regret, right? So this is a optimal. At least in the big O notation, it's a minimax nearly minimax optimal or minimax rate optimal. So whenever we talk about rate optimal, we are talking in this course. We're talking about this scaling in terms of the other parameters, modular, the universal constant, and sometimes the logarithmic factors. It matches the information theoretic limit, which means that no algorithm can minimize the max regret more than square root of tk. On the other hand, we've also seen through a gap-dependent analysis and we showed something that's significantly stronger for UCB in the sense that so I'm hiding the log t in the O2 parameter. We showed that the UCB algorithm automatically, without changing the algorithm, without knowing what these gaps are. So this delta A measures the performance of A star minus the performance of A, right? So UCB also satisfies this gap dependent bound, so that if there's a like constant separation between the performance of the expected value of the optimal action versus the all the other actions, then you can actually get constant regret rather than something that scales with square root of t. Okay, and in fact, these decisions can be made per action. So you can select an arbitrary subset of the actions and apply this bound, and for the remainder of the action, you can apply this bound. Therefore, like for UCB, we can actually get adaptive regret, which essentially says that it scales as square root of t multiplied with number of remaining actions. Or k minus a chosen subset of action cardinality. Okay, square root of this plus the summation of all a in a tilde and 1 over delta of a log t. Right. So UCB also satisfy a regret bound that looks like this, and in fact it is you don't need to like the algorithm doesn't depend on the choice of this subset of the actions. So you can in some sense choose any a tilde as a subset of the action space. Right. So this says that UCB is really simultaneously optimal and adaptive to particular easy property of individual instances of multi-bandit algorithms. So the analysis of UCB algorithm is revealing. So I'm borrowing this slides with from Sham and Wen. So the idea is that we can apply the concentration to achieve a uniform convergence bound for all the estimates that we get, right? So recall that UCB algorithm tries to estimate the expected reward. Tries to estimate the expected reward given all the information that's available up to this point through the empirical plugin, right? And we went into the details how we can apply a slight generalization of the Hostings inequality called a Zuma Hostings inequality, and by constructing a martingale. And then by the martingale concentration and the union bound, we can show that simultaneously for all action and all time point, then based on our estimate, plugin estimator of the expected value of individual actions, plus and minus the error bar, based on the number of times those actions are played, and with some additional logarithmic factors that makes it larger and holds with high probability. Then with probability 1 minus delta, then simultaneously over all these random variables, we know that the true value of the parameter are in between, are sandwiched in between the lower confidence bound and the upper confidence bound. Right, so graphically, you will have an error bar that's plotted, and the true value is like we don't know where the true value is. It could be bigger, it could be smaller, but it is always within this interval with high probability. And the UCB algorithm tries to stay optimistic by saying that we will choose the next action according to the upper confidence bound, according to the action that maximize this upper confidence bound. And this strategy allows us to bound the instantaneous regret, which is a difference in the expected value between the action, the optimal actions, the action that you take at step t. So we basically add and remove things. We basically add and remove the upper confidence bound of a star, and then also add and remove the upper confidence bound of a t. Right? Since the upper confidence bound is always larger than the actual value, then we can upper bound this with upper confidence bound of a star, and since also since that the AT is the maximizer of the upper confidence bound at time t, we can further bound this by this quantity, right? And lastly, we are left with the difference between the upper confidence bound of AT and the actual value of AT, and the actual value of AT is lower bounded by the lower confidence bound. Therefore, in total, we get 2 times error bar, right? We get the 2 times error bar corresponding to this action AT. Right. So this observations allows us to bound the instantaneous regret, and the total regret is a simple summation of the instantaneous regret. So yeah, I'm copying these from the book, which uses slightly different notation. So we use this instead of IT, we use the AT, which is action that we choose at time t. But other than that, everything is the same as what we as what we discussed. So just now we had a instantaneous regret, right? So we can bound every individual summoned here with a term that depends on 1 over square root of nt of AT. So this is a number of times that this action is taken, and then we can decompose this summation by partitioning it according to the value of AT, so that I can replace that with a double summation. And then then since that in every time this action is taken, the number of times actually increments by 1, then we got a series summation of 1 over I from I to nt of A. Right, and we based on this integral argument that we've shown in this epsilon greedy analysis, we know that this is smaller than 2 times the square root of nt of A, right, which gives rise to this bound. And it remains to simply apply the Cauchy-Schwarz to get the square root of to get the to get the square root of TK worst case bound, as we've shown. And for the gap dependent analysis, basically we can apply this lemma to bound this quantity, and then we can get a gap dependent analysis. And why is this true? And this is simply saying that whenever the upper confidence bound, which is the I think we used Q hat, Q bar of A is smaller than the actual value of A star, right? Whenever this happens, then then A will not be chosen ever again. The reason is that under the high probability bound, we are determining which action to take based on the upper confidence bound rule, and with high probability over the entire trajectory, this mu of A star is always smaller than our upper confidence bound of A star, right? Therefore, if this is smaller than mu of A star, then it is smaller than the upper confidence bound of the optimal action. Then there exists another action that's more preferred than this action. Then UCB will no longer choose this action ever again. So based on this argument and the fact that the gap between this and that is so mu of A star minus Q bar of A is always smaller than delta of A. And this is again because this is a Q bar of A is always an upper confidence bound of, it's always an high probability upper bound of the value of A. Then so these two observations together gives rise to a total number of pools of arm A that's bounded by 1 over delta A squared. So this is reasonable, right? This is reasonable because we know that by the statistical convergence of 1 over square root of n, then in order to get an error estimate that is proportional to delta of A, which suffices to certify the suboptimality of this action A, it suffices to pull the arm by 1 over delta square A times. Okay, well, hope that reminds you of some of the things that we did last time. right? The Azuma-Hofstadter inequality and martingale is essential for the analysis of MAB. So that wasn't explained very clearly in the book. But yeah, I hope that the extended treatment of the application to get those concentration helps you to understand the technical details of proving this algorithm works. Okay, so towards the end of the last lecture, we talked about linear bandits. We essentially only had time to set things up and then talk about the linear UCB algorithm. We switched to like for the convenience of me preparing for this set of slides and for you to refer to the AJKS book. So we switch our notation to this notation, which I believe is inherited from the original paper that studies the linear UCB. So this is Dani et al. I think 2008 or 2009. So they use this set of notation. So we'll stick to that. So the action space is now denoted by this letter D, so which is a compact subset of the R to the D, and individual decisions that the agent is supposed to take, we denote it with a vector xt. The reward is linear. By that we mean that the expected reward is linear. So the expected reward of this any action and like an infinite number of action is linear, which is given by an inner product of an unknown parameter vector, unknown parameter vector, and your chosen action x, right? And we assume that the reward is bounded between -1 and 1. So previously we assumed the reward is bounded between 0 and 1, but now like we only assume that the expected reward is bounded between -1 and 1. Okay, and we're using this eta t to denote the noise at time t, and we assume that this noise is independent and zero mean at each individual time. And now that the agent chooses a sequence of actions, we can define how we evaluate the performance of the agent. So as before, the regret is evaluated to be the expected regret. So this is the optimal action from the agent who knows what this coefficient vector is. You keep playing the same action again and again and again, and this is the expected performance that you get, minus the xt, yeah, sorry for the typo, minus the performance of your agent. So this is the expected performance of the expected reward of the performance given the sequence of chosen action xt, right? So the xt itself can still be the random variable. So we'll be deriving the high probability regret, right? And conversion to the expected value of the regret over the randomness of the agent is straightforward. So I'll leave that as an exercise for you to figure out how to deal with this. Okay, and X star denotes the optimal action, which chooses the optimal actions and maximizes the expected reward. And the linear UCB algorithm follows the same principle of optimism in the face of uncertainty by constructing an empirical estimator based on the observed rewards in everything in the past, and then by running a ridge regression. And once we have that, we'll have a high probability confidence bound of the parameter vector that's specified to be an ellipsoid. And while the actions correspond to one that maximizes the upper confidence bound of the confidence set of the parameter vector converted into the confidence bound of the individual reward. individual expected reward. So let's revisit this algorithm and make sure that everybody understands how the algorithm works before moving to the analysis. Okay, so we'll consider ridge regression. Which says that we're gonna be estimating by solving the regularized least square problem. So this will be our arc mean of this objective function, and the objective function is xt transpose theta minus the reward t square plus lambda theta square. Yeah, let me change the index I from 1 to t minus 1. Okay, and lambda is a parameter to be chosen, and xi ri is a sequence of for I from 1 to t minus 1 is the entire transcript of your algorithm at this point, so far at time t, right? So these are the feedback and the actions that you've taken like up to this point, and we can come up with a ridge regression estimator. Okay, so there's also a matrix form that's worthwhile writing down. So this mu hat of t is also equal to arg mean of if we concatenate this matrix to be x1 transpose to xt minus 1 transpose. So this is a matrix of t minus 1 by d, right? So if we do this and then this simply becomes the standard formula that you're familiar with, transpose theta minus let's also call this r t vector to be the r1 to r t minus 1 in r of t minus 1 minus r square plus lambda theta star. So it will be clear to you that there's a closed form solution for this, which is given by xt xt transpose xt plus lambda I, where I is identity matrix, inverse x x transpose times x transpose times this r vector, right? And we call this matrix, so without inverse, we call this matrix the sigma t matrix. Yeah, so it is a regularized I guess uncentered covariance matrix of the observed sequence of design points. Okay, so once we have that, how do we construct a high probability confidence set? So the high probability confidence set of interest. So this is a this is a parameter space which they call ball t. Ball t is equal to the set of all parameters such that mu minus mu hat of t transpose sigma t mu minus mu hat t. This mu hat t is a ridge regression estimator, and this is coming from this matrix, smaller than beta t. So beta t is a sequence of parameter of the algorithm. Okay, so lastly, so once we have this uncertainty set of the ground truth parameter based on things that we've derived so far, and in every time t, we're choosing this action xt to be the arg max of all x in this decision set, and max of all possible mu in this version space called ball of T, and inner product of X and mu. This is a bilinear like optimization problem with convex constraints. So this is the ellipsoid, and this is an arbitrary compact set. Yeah. So even if this decision set D is a convex body, then the solving this is actually an NP-hard problem. So there are instances of this problem that is computationally inefficient. On the other hand, like we're going to be analyzing this, and there are like alternative algorithms that uses relaxation to this set. In particular, instead of using an ellipsoid, you can use an L1 ball. Which in those cases when this decision set D is convex, you can convert this into a problem that's computationally more efficient. Okay, at a cost of a slightly worse dimension dependence. But yeah, there are like computation statistical trade-offs that we see here, and we're not covering that. We are analyzing this particular algorithm. And how do we understand this? So this is an uncertainty set of an ellipsoid centered at eta. So now what I'm gonna do is to let's say that let's say that the decision set X is anything in the Euclidean is everything in the Euclidean ball or like, yeah, it depends on what this D is, but if X is if X is X is a unit ball, like if D is a unit ball, then you can basically try aligning this X. Let's say that this is origin and this is the vector. You can basically try out the different possibilities on this ellipsoid. Take the inner product and then find the one that gives you the largest expected reward. So what this gives you, is an optimistic estimate of the expected reward given this action X. Okay, so that symbolizes this principle of algorithm design optimism in the face of uncertainty, right? In this case, uncertainty is not directly on the reward, but on the parameter vector that can be used to calculate the reward, and that certainly propagates into uncertainties on the reward, expected reward for all rewards simultaneously. All right. So in this lecture, we're going to analyze the regret of the Lin UCB, which is a somewhat longer analysis than what we have covered so far. But we'll get through it. I'll explain it as clearly as I can. And then we will set up the problem for exploration in tabular MDP and then explain this algorithm and how we can extend the idea of optimism to learning to reinforcement learning. Okay, so we start by stating the theorem. So this is the regret bound of the Lin UCB algorithm that we specified just now. And what this says is that if we choose this regularization parameter lambda of the ridge regression according to this formula, and if we choose the sequence of the beta t parameter, so in fact this doesn't depend on t, it only depends on the total horizon capital T, it only depends on that. So if we choose beta t to be this quantity, then with high probability, the regret satisfy this expression with a universal constant, linear in the noise parameter, and square root of t. Yeah. So notice that they are assuming boundedness of the noise for simplicity, and you can actually get away with the sub-Gaussian assumptions. You can basically assume that this eta t is independent, and sigma square sub Gaussian. Okay. So here's the statement. The important things to note is that this is proportional to outer square root of t, right? So you have sublinear regret, and it generalizes over the multi-arm bandit setting at least in the sense of t.
So Xiang, this
Yes.
beta t does not depend on t here.
Right, the beta t doesn't depend on the t. This is not an anytime algorithm. You can use doubling trick to convert this into an anytime algorithm. So beta t, so at the moment depends only on this capital T parameter.
So we can replace it with some inverse dependence on t, so that the confidence region sort of shrink as time proceeds, right?
Yeah. So this is a multiplier to the confidence region. So the confidence region will shrink. So let's go back. So what is a confidence region? So the confidence region will really shrink as the magnitude of this sigma t gets larger. So notice that this sigma t will get larger and larger since sigma t is equal to the sum of the like small x I transpose from I to t minus 1 plus lambda I, right? So as we collect more points, then on the right notion of this geometry, then the magnitude of this quantity is getting larger. Therefore, this ball is getting smaller and smaller and smaller.
Got it. Thank you.
Yeah. So yeah, due to that, like the constant multiplier of this, like this can be set as something that's more or less fixed.
Yeah. Thanks.
Okay. Yeah. Good. Yeah. Excellent question. So yeah. So of course, as we keep learning, we expect the confidence region or the version space that traps the underlying true parameter to be getting smaller and smaller as t gets larger. Yeah, that's not reflected on beta t though. All right, so the regret analysis has two main like lemmas that we need to prove, and once we have this lemma, then it is relatively easy to prove the regret. So the first thing is the concentration analysis. Right. So the first thing that we need to show is that for these for appropriate choices of beta and lambda, then the true parameter is always within this ball with high probability for all t simultaneously. So notice that this is a uniform convergence bound. So it requires that this holds for all t for all t in 1, 2, 3 to positive infinity, that this is this high probability event holds simultaneously. Okay, uniform concentration. Okay, and the second bound that you need is something stronger than the regret bound, which is the sum of the instantaneous regret, and what you can prove is actually the sum of the squares of the instantaneous regret is bounded by something that's more or less independent to t. It depends on the logarithmic in t, right? So so we define the instantaneous regret to be the oracle's performance and the performance of your agent, right? So the parameters here says that the diameter of this decision set D is bounded by B. It is bounded by parameter B. Okay, so the first thing that we're going to do is to make use of these two propositions and then show that this actually recovers the regret that we stated in the previous theorem. Okay, so the idea is quite straightforward. It simply follows from the Cauchy-Schwarz inequality, and then by substituting this beta parameter using the beta that we choose. right? So to apply Cauchy-Schwarz inequality, this is summation 1 multiplied with regret, right? This is smaller than the square root of sum over 1 square plus the sum over multiply with the sum of the regret t square, right? So this is standard Cauchy-Schwarz, and then you get t from here, and then you get the sum of squared bounds here. Yeah, so this is a standard trick. And once we have that, we can substitute the sum of the square regret bound, which was the second proposition from the last slide, and then get that. And it remains to substitute the choice of beta t, and we've seen that beta t is this quantity, right? So it is it's somewhat complicated. It's a sigma square 2 plus log 1 plus t beta I guess d lambda, and I think there's another term, right? So let's go there. And okay, there isn't a lambda here. There's a leading factor of d in front, and a times log 4 over delta. Over delta, and there isn't a lambda here. I think there's a dimensionality dependence there, right? So if we substitute beta into this expression and then simplify the expression a little bit with basic algebra, then you can get that the bound you can get that the bound that you achieve is something like this. Okay. Now, how are we gonna proceed with the proof? Like there are basically two main components. The two proposition. One is to analyze the concentration by establishing the uniform confidence bound that the sequence of version spaces actually always trap the true mu star parameter inside, right? So that's the second step that we're gonna do. But before that, we'll first prove the second proposition that bounds the sum of the square regrets, right? So we'll do that by first bounding the instantaneous regret and then bounding the sum of the square of the instantaneous regret through a trick that first so through a trick that does a logarithmic transformation and then tries to bound the same quantity and constructing a nice structure that allows us to bound the information gain. So yeah, it will be clear like what I mean by information gain, like in just a few moments. Okay, so we'll need a number of lemmas to proceed with the analysis. So the first is a bound on the performance of in some sense for for all possible parameters in the current version space, what is the what is the performance difference comparing to the comparing to what is the performance difference like that's measured like when you when you consider your estimator to be the true parameter, right? So this should resemble the like differences of the expected regret, except that the mu star isn't in the picture, right? So you can think about this as a natural width of the confidence bound restricted to a particular direction x. Okay, so we'll see that it can be measured by some like ellipsoidal distance, like measured in terms of this with a leading multiplier of square root of beta t. Okay, so let's prove this. So so the first step is straightforward. So you multiply with this matrix and then invert with this matrix. Multiply this matrix inverse. So you add these two things in the middle, and you can always do this because this matrix is positive definite. Say recall that this is equal to sum over I xi transpose from 1 to t minus 1 plus lambda identity. So this is positive semi-definite, and this is positive definite. Therefore, this is positive definite and invertible, right? So you can take the square. You can take the square root. So the square root is essentially taking the square root on every element of the eigenvalue of this matrix, and then multiply everything back. And you can also take the inverse of that, and this is well defined. So once we have that, we can we can group this together. We can group this together and group this together, so this becomes a simple inner product of two vectors. And then we can apply Cauchy-Schwarz inequality, which gives you the two norms. So in general, when you have an inner product of this form, then you can bound it by A norm and B its conjugate norm. And in this case, we're taking both norm to be the Euclidean norm, which is the sum of the individual elements, square, right? So yeah, an alternative way of thinking about this is that this is actually the mu minus mu hat t epsilon t sigma t norm, and this is x sigma t inverse norm, and these two are conjugate, so you can get the same expression through Holder's inequality of instantiating a slightly different norm. Okay, so the next step is then to right, so yeah, essentially doing what I've already said by converting this into x transpose sigma inverse x, right? And this is what we want, and the last thing is to bound the last thing is to bound this property, right? So we get that using the definition of this ball. So ball is defined again defined to be the set of all mu such as mu minus mu hat t transpose sigma t. Mu minus mu hat t is smaller than beta t, right? Therefore, so this is a square of this norm, and you end up getting square root of beta times this quantity. Okay. Now with this, we'll define the width at time t corresponding to the chosen action by the agent xt. So let's just get rid of this square root of beta t parameter and call this the width of x corresponding to that special ellipsoid that we construct. So this is normalized in the direction of the decision. It's normalized since we've gotten rid of this beta t multiplier, and then we can bound the instantaneous regret by this expression, right? So what do we do? So first of all, let's call this mu tilde to be the minimizer of mu tilde transpose x when mu tilde is inside this ball of t. Then we know that for this particular choice of xt, right? For this particular choice of xt, and also for this, and also for this argmax of mu tilde xt, then this is always this is always larger than that of the optimal choice. Okay, so x star and mu star, they are feasible solutions to this. So when we substitute the optimal choice of mu tilde and then xt by first solving xt and then solving this mu tilde, then this like then you always have this inequality based on the fact that we are maximizing this quantity. Okay, and this inequality implies that we can bound the regret by substituting this mu tilde x star by substituting this mu star transpose x star with mu tilde transpose xt. Okay, so this becomes something that we have proven in the previous lemma that we now know what to do with. So so once we once we have this, we basically use the again use our standard trick of adding and removing the mu hat. So this is the centroid of your ellipsoid. And once we do that, and then we'll invoke the previous lemma for both terms, right? So we'll call lemma 5.7 here and call lemma 5.7 there, where instantiating that arbitrary value mu to be mu star and mu tilde separately, and the multiplier of 2 together with the bound that we got before give us square root of beta t times this normalized width with WT. Okay, so that proves this inequality. So how about the second inequality? Yeah, this is really to simplify the expression a little bit, and it requires an additional assumption. So this requires I guess two assumptions. The first assumption is beta t is non-decreasing in t. So as t gets larger, this sequence of beta t's is always monotonically increasing. And the second requirement is that the beta t is always larger than 1, right? Beta t is always larger than 1. With these two conditions, you can extract the square root of beta t out while only making making the first term larger, right? So these two assumptions were stated. So let's go back. Let's go back to the let's go back to the theorem. Yeah, so these two conditions are satisfied based on this choice of beta t, right? So under some yeah, do we need an additional condition? So yeah, we might need an additional condition saying that this sigma square parameter is not too crazily large, and for this beta t to be greater than 1. But other than that, like these are the mild conditions that we assume to simplify the expression a little bit. Okay, so let's go back to what we've proven here. Okay, now that we have an instantaneous regret bound, and we will just put everything together and then try to bound the sum of the square instantaneous regret bound, right? And the argument to do that requires us to consider a potential function, and then the logarithmic transformation of things that we'll see that will become quite handy, right? So let's take a closer look at this. Let's take a closer look at this unnormalized the covariance matrix in terms of the right natural geometry that we can measure it, right? So this DET means determinant, which is a product of the eigenvalues of a given matrix. So we will establish that the determinant of the t step is decomposes into the product of these individual quantities, and we can actually bound the determinant of this covariance matrix of the t step with a product of T quantities that depends only on the width. Okay, so let's see how we can prove this before we make use of this lemma to prove the sum of the square regret bounds. So we'll prove this by induction. So we'll first say we'll first try to prove this recursive expression that tries to bound sigma t plus 1 using sigma t. Okay, so so the first step simply follows from definition. In every step, we're adding this xt transpose to your previous steps unnormalized, uncentered covariance matrix, and then we can and then we can split this and then we can split this up by multiplying by splitting this sigma like sigma t into 2 halves. So we've seen like why this is possible, and this is because sigma t is always strictly positive definite. So we can take the square roots of this matrix. So again, square root of this matrix is equal to, let's say that this matrix follows from a eigenvalue decomposition. Then the square root of this is simply the square root of each individual eigenvalue. So if we do that, we can split this into 2 halves, and then we can multiply the inverse of that to the second term, and that gives me this expression in the middle, sandwiched in between, and then by the property of the determinant, we can always wrap those matrices around, right? We can wrap matrices around. We can put this to the other side, and then that gives me the determinant of the 2 different matrices. And once we have that, we are representing the determinant of sigma t plus 1 using the determinant of sigma t together with this increment, and we will call we'll call this vector bt. Okay, observe that vt transpose vt. So what is it really? So vt transpose vt is equal to xt transpose sigma t minus half, and this is symmetric. Therefore, I can drop the transpose sigma t minus half xt, and this is precisely our definition of this normalized with wt. Wt squared, right? So substituting this into substituting substituting this into this determinant. Yes, if we substitute this expression into the determinant, so notice that why are we doing this? We want to calculate the determinant of I plus this vt transpose, and since vt satisfies this, we can divide this by vt. So this is equal to vt square norm. We can divide this by that. Multiply with vt square and vt transpose divided by vt that. So this becomes eigen decomposition. This becomes of eigen decomposition of this rank 1 matrix vt transpose, with the eigenvectors being the unit vector. Therefore, when we use the same eigen decomposition of the full matrix I plus vt transpose, then we get an eigenvalue that is 1 plus vt square and 1 1 1 1 1, right? So those will be the eigenvalue of this whole matrix, and the determinant of this whole matrix would then be the product of all ones together with 1 plus VT square, which we've shown that it is 1 plus the WT square, right? So that gives us the recursive part of the induction. And clearly the base case when T is chosen to be 1 is straightforward, right? So we can set we can set the sigma 0 to be just lambda identity, right? Which gives us a base case. Then by induction, we can get this expression for all T. Okay, so the idea is that this eta T is a summation of xi transpose plus lambda I, right? So this is a summation of these matrices, and by taking the determinant and then by this decomposition of the determinant, we can convert this summation into the product. And sometimes the products are easier to handle than the summation, especially after we take log. Okay, so why are we proving this, and how can we make use of this? So as I said, we can take the logarithm, and when we take the logarithm, then we can when we take the logarithm of the two determinant, then we end up getting the differences between the two log determinants. So the log determinant in a multivariate Gaussian case is given us the entropy. So the differences of the two entropies gives us the information gain, right? So the interpretation of this as information gains is coming from the Bayesian perspective that considers that considers the sequence that's chosen by the agent is coming from some kind of a distribution that's multivariate Gaussian with a covariance matrix that's proportional to this sigma parameter, right? So let's prove this lemma, and then before we plug in this lemma to bound the sum of the square regret. First of all, we can apply the first of all, let's denote the eigenvalue of this unregularized covariance matrix to be sigma 1 to sigma d, and the sum of those are traces of this quantity, which is the same as the sum of the eigenvalue of this is the same as the Frobenius norm of this X matrix, right? So X I guess sigma I. Okay, sigma I of X transpose X sum over sigma is the same as the X Frobenius norm square. And this is the same relationship by saying that this is equal to trace of X transpose X. Okay, and since that we assume that individual xt is always bounded by B, then we can bound the total of this quantity by T times B squared, right? So again, we're just getting some crude bound of the trace of these matrices. Okay, and well, what are we what are we doing here? So notice that when we divide both sides by the determinant of sigma 0, then we get a product of 1 plus WT squared. right? So this is what we are. Um, so this um, so what we do in this expression is to, since this is determinant, and determinant is a product of product of the eigenvalues. So now that we've defined this sigma i's to be the eigenvalues of this expression, then we can write it in terms of the eigenvalues themselves, right? And these are the product of the eigenvalues. So what we can do is that we can we can take the 1 over d, and then on the outside take it to the power of d, right? So this is a straightforward transformation, and then the d that's outside, since there's a logarithmic transformation in front, we can extract this d outside. So what is inside the logarithm is a geometric mean of these quantities 1 plus sigma I over lambda. Okay, and then using the algebraic mean geometric mean inequality, we can bound this using the algebraic mean. So this converts the term that's inside the log to be the summation over these quantities, which further allows us to use a trace to bound this quantity using using tb squared, like over d lambda. Okay, so what are we doing here? So notice that this is something that's actually quite nice, because previously we have things that got multiplied together, and we have this we have this quantity that is a summation of the t values. But ultimately, we can bound the information gain like by something that depends only logarithmic in t. And that is critical for us to provide a strong bond of the sum of the square regrets, right? So it follows from this sequence of argument. So first of all, just now we've bound the we've bounded the regret with this expression, and so this is lemma. It's just this lemma. Right, so we're using this lemma to bound the regret. So if we're taking the square of this term, then we got beta t, and then we got the wt square. Okay. So that's by invoking this lemma, and then we can always replace this beta t with beta capital T, like due to the fact that the beta t is monotonically increasing. Right, so in the algorithm is actually set as a fixed parameter. So this is equal. Okay, so what happens next is to apply this inequality of log 1 plus epsilon is always larger than 1 minus epsilon and smaller than epsilon. So what this is saying is that the log looks like that, right? So log looks like that. It is always lower bounded than it is always lower bounded by this, but it is always also upper bounded by something that goes to 0 even faster. As epsilon approaches 0, and of particular interest when yeah, I think this is plus log crosses 0 at 1, and then this is yeah, let me redraw this figure. Yeah, this can be proven algebraically by Taylor's series expansion of log 1 plus x. So the horizontal axis is epsilon when epsilon is equal to 0. So log 1 is 0. and when and it looks like that, and when epsilon is -1, this becomes negative infinity. So this upper bound on the right hand side is straightforward. It follows from by the concavity of log 1 plus epsilon and the linearization at 0, right? And for this one, in particular, it implies that when epsilon is larger than minus half, then this is larger than it's smaller than when epsilon is smaller than 1, then this is larger than half of the epsilon. Okay, so under some additional conditions, you can sandwich log 1 plus epsilon with quantity that's linear epsilon on both sides, right? So now let's try continuing this argument and simplify this expression further, and then make use of the information gain lemma that we've proven just now. Okay, so what we're gonna do is to bound this quantity by, I claim that we can bound this quantity by the maximum of 8 and 4 over log 2 beta t and summation of t from 1 to t minus 1 log of 1 plus wt squared. Okay, so why is that the case? First of all, let's discuss two cases, right? So this is a minimum of wt squared and 1, right? So when wt squared is smaller than 1, then this expression is simply wt squared. Then we can use use this expression, right? We can use this inequality. Right, so when the wt squared is smaller than 1, then wt squared is what is active. Therefore, it suffices to multiply this leading constant by a factor of 2 in order to use the log 1 plus x to bound log 1 plus epsilon to bound epsilon. Okay, so that gives rise to this 8. So in the alternative case, when wt squared is larger than 1, then 1 is active. Right, then 1 is active. Then we're basically trying to bound we're basically trying to bound just this 1. So in this case, when this is active, we can like make use of this then log 1 plus wt squared. So this is always larger than log of 2, right? So this is because wt squared is always larger than 1, right? And if we can do this, that means that this expression in this case can be bounded by log of 1 plus 1. That is true, right? So it suffices that we divide this log 2 and multiply this log 2 and then relax this log 2 to log 1 plus wt squared. Right. So this gives rise to the second constant here. So in particular, 4 beta t is smaller than 4 over log 2 beta t times log 2. This is equal to this. And smaller than 4 over log 2 beta t log 1 plus wt squared. Right. So in both cases, we can bound this expression using using a constant multiply with this log 1 plus wt squared term. Okay, so this simplifies things quite a bit, and we can like recall that in this lemma, right? In this lemma here, then we can rewrite this since this is an equality. We can rewrite this, and using the fact that the summation of the log becomes the product of these quantities, we can write this as this leading constant beta t of log determinant of sigma t over the determinant of sigma 0. Okay, and by the bound that we got previously in the second lemma, by this bound, we can further bound it with c beta t and d times log 1 plus t b square over d lambda, right? And that concludes the proof for the sum of the square regret terms. Okay, so so it remains to bound the uniform confidence. Okay, so we will take we'll take 4 minutes break and we'll resume at 2:22. I'll see you guys in 4 minutes. All right, it is about time. Let's resume the lecture. So we will finish the proof of the regret analysis for Lin UCB. So far we've we've proven like two of the proposition, the second of the proposition, which bound the which bound the sum of the square regret under the assumption that that mu star is always inside the version space ball t for all t simultaneously, right? So so we know that the sum of the square bounds implies by a simple Cauchy-Schwarz argument implies the square root of t regret bound on the sum of instantaneous regret itself. And the trick that we use to the trick that we use to construct this bound is through a potential function argument by constructing the log determinant of the covariance matrix, and then like we essentially bound this this information gain using something that's completely independent to the choices of the algorithm, right? So the right hand side is completely independent to the choice of specific xt. So the only information that we use about this sequence of xt is their boundedness, and this is okay since everything is only inside the logarithm, right? And which grows very slowly with t and also with b parameter, right? So this is kind of nice, and we convert something that involves the summation of t terms into something that happens only in the logarithm. Okay, so it remains for us to show that the choice of beta t is sufficiently large, such that the mu star is always in bt in ball ellipsoid at every step t for all t equals to 1, 2, 3 to infinity. Okay, so how do we go with the argument? So recall how we are constructing this version space. How are we constructing this version space ball T? It is really by solving a ridge regression and then find an ellipsoid in the neighborhood of the ridge regression fitted coefficient mu t hat, right? So in order to prove that this actually works, we need to analyze the ridge regression and show that under our data generating model that this is actually giving us something that's close to the ground truth parameter, right? So the sequence of our argument on the high level, like really, is to decompose the bias and variance, and then substitute in the data generating data generating assumption. Okay, so the first thing is by definition. So recall that this is equal to the matrix x xt transpose xt plus lambda I, right? So and this summation and this summation of x tau r tau from 1 to t minus 1. Yeah, I guess they're using the 0-base index. This is the same as the as this x transpose xt transpose of our vector, right? So you get this ridge regression closed form solution, and then the second step is to adding the definition of RT by this data generating distribution, right? So you have the expected value to be linear in xt inner product with a true parameter plus this additional like sub-Gaussian noise, and then we can then we can group this then we can try grouping this mu star parameters together while like grouping the rest of the parameters that's related to the noise. right? So we can just multiply this xt inside and then group this xt transpose term together, and look what we have. So this is this is similarly the empirically observed covariance, the empirically observed covariance, um, and and uh, what we got here is let's write it down. So we have x, we can xt transpose x plus lambda I inverse, and xt transpose xt, right? So this is xt transpose xt, and this is the definition of the sigma t inverse, right? And this one, I'm gonna add lambda I and subtract lambda I, right? So this gives me identity minus lambda sigma inverse, sigma t inverse, right? And notice that this got multiplied to this mu star, right? And then there's a subtracting mu star here, which cancels with this identity multiplied with mu star. And what this and what this gives me is the is this expression. Am I missing a minus sign? So let me check. So I'm adding this, I'm subtracting this from here. Yeah, not actually. I think it is a book that is missing this minus sign. So there should be a minus sign here. It really isn't affecting the analysis. But what we got here is that this is a bias term, and this is a corresponding variance term. The noise term that is zero mean, and its magnitude correspond to is proportional to the square root of the variance, and we also see that it has a nice structure that is so notice that this eta t, they are independent, right? They're independent and sub-Gaussian, so they follow from a summation of independent random variables, right? So then what we want is to bound to find the parameter with the smallest beta t such that this mu t is trapped in this ball. So notice that we want this to be smaller than beta t. We want to choose the beta t such that this is sufficient. So we need to bound this quantity. So we will substitute this expression of the difference into this, and that by triangular inequality decomposes into the two parts of the norm. So again, this is bias, and this is coming from a variance, right? So it suffices to provide a high probability upper bound to the variance term. And how do we do that? So again, notice that these are summation of the random variable, but what makes it tricky is that these xt are actually chosen according to previously realized the randomness. So instead of the summation of the independent random variables, so these are the independent random variables multiplied with some other deterministic choices that depends on the previously realized independent randomness. So what is this then? It's a martingale that we talked about last time, right? So how do we analyze this? So we could potentially try using the Azuma-Hofdings inequality and leveraging the fact that this xt is bounded. But then that will give us bounds that actually depends on the smallest eigenvalue of this this sigma t parameter, right? Which is something that we don't really want, right? We want something that's more condition number independent. And the trick to do this is to invoke this advanced version of the martingale concentration bound, which says that if you have a sequence of like independent random variables, so these are our eta t's. These are our eta t's. If you have a sequence of independent random variables that are bounded, right, rather than sub-Gaussian, but the similar argument works for the sub-Gaussian assumption. But if they are bounded, then you can construct this self-normalized type of martingale concentration bound, which says that under this geometry that's given by this xi's themselves, then you can bound this using again the information gain. Yeah, this is nice because we already have bounds that can be used to bound the log information gain, and the kind of bound that we get is completely independent to the conditioning and how large the largest eigenvalue or the smallest eigenvalue is for these matrices sigma t, right? So this is something that we know how to handle, and now we have a high probability bound. Yeah, by substituting this bound into the previous expression, then we get by substituting the bound into the previous expression, then we get this, and then by further substituting the by further substituting the bound of the log determinant, the log determinant of the ratio. So this part is the information gain. That we have a bound of log 1 plus t b square over lambda, right? So this is something that we know how to do. So it remains to deal with this delta t. It remains to deal with this delta t parameter. So notice that this is a failure probability. This is a failure probability that will apply to every t. Right? So we want this to hold simultaneously for all t. Therefore, we need to choose a sequence of delta t parameters so that the summation of them by the union bound gives us some finite number, right? So it suffices to choose this delta t to be proportional to this quantity. Yeah, I think they missed this multiplier delta. And once we have this, we can apply the union bound. Can apply the union bound and then bound everything with this, multiply with this parameter delta. And what is the quantity here? So it is a constant, and then the sum of 1 over t squared, right? From t to infinity. Can anyone tell me like what the value of this is? It's equal to pi square over 6, right? So that is the reason why we choose this 3 over pi square in the first place, and this gives us gives us half multiplied with delta, right? So in fact we can choose this to be delta. Yeah, I guess we can choose this to be 2 times delta, right? 2 times delta equals to delta. Okay, and well, so there's this bias term that we also need to deal with. And what do we do there? So the only thing that we need to realize is that this is the smallest eigenvalue of this sigma t is always larger than lambda, and this is because sigma t is equal to sum of xi transpose. This is positive semi-definite plus lambda I, right? So the smallest eigenvalue of sigma t is always larger than lambda. Therefore, the operator, therefore the spectral norm, the largest eigenvalue of so the largest eigenvalue of sigma t minus half. So this is smaller than 1 over square root of lambda. by substituting this bound into, first of all, why this is useful. So whenever we have this largest eigenvalue or largest, in this case, eigenvalue is also the same as a singular value for this matrix. So the spectral norm implies that for any x, a of x is smaller than a's sigma max of a multiply with the Euclidean norm of x, right? So that is a definition of operator norm, and when we have a large bound on the largest singular value of a matrix, then we can simply construct such crude bound that says after transformation of any vector by this matrix, then the amplification of how much this transformation makes this this vector larger is bounded by the like largest direction that this matrix can amplify any vector. So by simply applying this, then we can bound this by lambda multiplied with 1 over square root of lambda and then the mu star. And this gives me the bias term. Okay, so altogether, like these tells us that we can choose. This tells us we can choose beta t to be basically these quantities. So yeah, so I don't know what's going on because the beta t was what they specified earlier in the main theorem, but if we specify it in this particular way, so even though the information gain term is independent to independent to t, there's still this delta t parameter that we can choose according to the t. But this is like a relatively easy term to handle because it is straightforward to show that when this delta t goes to 0 and gets smaller as t increases, then beta t is a non-decreasing sequence. So it doesn't break the arguments that we used previously. Okay, so this wraps up the proof by leveraging this bigger hammer that allows us to create to bound the martingale that we got from decomposing the bias and variance of the ridge regression estimate, and that allows us to bound the distance between the ridge regression estimate and the ground truth in the natural norm that's specified by the sequence of action that we've taken. Okay, so that wraps up the proof. Overall, we've seen that the regression, the regret of the high probability regret of the linear UCB is proportional to d square root of t, and this is actually optimal. So no algorithms can solve the same problem within the family of linearly expected reward and sub-Gaussian case better than linear UCB up to this rate. We didn't talk about the we didn't talk about the gap independent analysis because in this case there really isn't any gap. So we're not making any assumptions about what the underlying geometries are, but it is making use of an potentially inefficient oracle to choose the individual actions. If you can solve that problem, then this is the rate that you can get. If you can read the original paper by Danny et al. They propose an alternative algorithm, algorithms that use a different oracle, and that algorithm is shown to be computationally efficient in some cases, and in those cases you can get a slightly worse regret bound of d to the power 1.5 square root of t with different but efficient algorithm. Okay, So let's take a step back, right? So we're making in order to obtain this regret bound, and the kind of argument that we've been using, like rely heavily on the fact that this is a stochastic setting, and also the expected regret is actually linear in some parameter. So it requires a good representation of the action that makes the expected reward linear. So that's not always easy to achieve. So one may ask a question of does so we've already talked about in multi-arm bandit there are adversarial style non-stochastic multi-arm bandit that allows a sequence to be arbitrary while the algorithm can compete with the best single action in the hindsight, regardless of what the sequence of reward is. So there's an analogy of that in linear bandits as well. So you can define the regret to be the regret to be the max of all mu within some parameter space, and mu and then the expected or I guess the sequence of regret by choosing the actions by choosing the actions according to mu, right? So we can potentially compete with this regret of. So this is your agent's performance, and this is a performance of the best linear policy, right? This is a performance of best linear policy. So there are algorithms that can actually show that such an adversarial notion of regret is also proportional to d square root of t. And two algorithms that achieves this is EXP4. So this is a exponential weighted algorithms for exploitation and exploration with experts, where these individual experts are certain discretization of the linear space of the family of our linear policies. And another algorithm that works on the stochastic setting, which says that this rewards somehow are generated in every iteration is stochastic, actually applies to a slightly different setting that's related to linear bandits. But there are algorithms that can achieve the similar like adversarial similar agnostic regret bound without assuming that assuming that the expected reward given x is equal to some mu star transpose x, right? So if you do not assume this, you could still compete with the best linear policy in the hindsight, and in the adversarial case, you can run the EXP4 algorithm, and in a contextual bandits setting with a stochastic like sampled reward, but not necessarily linear, then you can get the same regret with an algorithm called taming the monster by Arga 2014. So that's all I wanted to say about linearly parameterized bandit. So it handles a very hard problem with an infinite number of actions, and we studied it in a simple stochastic setting when the function class that we are given is realizable, which means that expected reward can actually be captured by the family of linear functions that we have access to. And in this case, we've formally derived its regret bound and show that the linear UCSB is a no regret learning algorithm that achieves the optimal rate. Okay, so in the remainder of today's lecture, so I'll only spend the next 3 minutes just setting up the problem of what we're going to be talking about on Monday. So we will be talking about exploration in reinforcement learning, and this problem, as we talk about, it is challenging precisely due to the need of exploration, right? So comparing to the bandit setting, which we always have access to all actions, so we can take any actions as we wish. So in the Markov decision processes, we cannot actually visit like a state arbitrarily as we please, because we do not have access to this generative model, and we might have to take a strategic sequence of action in order to visit a particular state, yeah, with sufficiently high probability, right? And precisely because of that, the data needs to be actively collected, and which breaks the independence assumption of the generative model setting. And that makes it substantially more challenging than everything that we've studied so far. So we will consider two settings. So one is the tabular Markov decision processes with the finite state and finite actions. And then after we talk about the tabular MDP, we'll talk about the linear Markov decision processes, where the state transitions and the rewards are all linearly parameterized by some unknown parameter vector theta. So different from our previous analysis of the generative model setting for the Markov decision processes, in this part of the class, we'll be focusing on the finite horizon episodic Markov decision processes, which will which we discussed briefly in the third MDP physics lecture. So there's a state space, action space, a system of transition kernels that are time varying that depends on H. There are also expected reward functions that depends on it depends on individual time step H. So the capital H denotes a horizon, and the mu is an initial state distribution. All right. So besides this, there are other notations. So as we talk about in finite horizon Markov decision processes, the Q function is indexed by T, right? So there are Q star T function, which is the max over all policies of Q pi of T. And obviously Q pi of T is to say that at step T and subsequently I'm following subsequently I'm following this policy pi to take all the subsequent actions. So similarly, there are this VT pi and VT star functions that's indexed by T as well. So when we talk about the policy, we naturally represent the policy that's a tuple of pi 1 to pi h. So at every time step, the policy is non-stationary. But even though it is non-stationary, it doesn't take the entire history into account. It only depends on the current state and the time index, right? So it's still somewhat manageable. So we need to learn H like different policies for different time steps. But it becomes natural and convenient as we will see in the exploration algorithm for finite horizon MDPs. All right, I'll stop here. We'll talk about the algorithm for online learning for finite horizon MDPs in the next lecture, and also prove its regret. Also set up what we mean. What do we mean by a regret in learning MDPs, and as well as providing the technical details on how we can analyze such algorithm by following the same principle of optimism in the face of uncertainty. All right, yeah, thank you guys for coming to the lecture, and we'll stop now, and I will see you guys next Monday.